Okay, thank you so much. Good to be here. Yeah, so I'll tell you a bit about effectful programming in the Flix programming language. So to start with, you may be familiar with imperative programming, object-oriented programming, probably with functional programming since you're here today. And so I'll be talking about effect-oriented programming and in Flix. And so in the same way, if I wanted to teach you about object-oriented programming, I would probably need a programming language with objects in it. So to talk about effect-oriented programming, well, I need a language with effects, and so that's the Flix part. And I'm saying if you love types, then you're going to love effects. Just before we get started, this is not just my work, it's also work by my PhD students, Matthew, Jonathan, and Andreas, and our compiler engineer, Jacob, and also all our open source contributors. Okay, so let's talk about effect-oriented programming in Flix. So what is an effect system? Well, it's something that tries to describe the actions that our program can take. So when we run this function, for example, what can it do? Does it access the network? Does it access the file system? Does it mutate something in the heap? And why would we care about this? Well, first of all, if we know the effects of a function, that can help us understand how the program is behaving. Second, well, maybe there are certain effects that shouldn't be allowed at certain places in the program. And so we can use the effect system to say those are forbidden here, and so get more static guarantees. Finally, if the compiler knows something about the effect behavior of the program, it enables compiler optimizations. So those are three reasons to care about effect systems. So just in one slide, well, what is an effect system? So here is a function called f, takes an argument x, and then it divides that by the current minute. That is a simple function. If we have a type system, it could tell us that, okay, x is an integer here, and f is actually something that has the type int to int. But an effect system would give us some more information. Potentially, it could tell us that actually this function is non-deterministic. So even when given the same input, it could return a different result. And that's, of course, because the current minute is changing. It's, minute 1, minute 2, minute 3, and so on. And it could also tell us, actually, the current minute could be 0. When the clock is 0, and we could get a division by 0 exception. So an effect system complements a type system by telling us about these actions. Okay, so let's talk about the Flix effect system specifically. So in Flix, we can define a function that takes two integers and returns an integer. And then here, after the return type, we have the effect of that function. And so one thing we can track is that we can say, actually, this function has no effects. And so that means that this function cannot do anything other than computation on its input. It cannot access the network. It's an ironclad guarantee that there are no side effects. We can also enforce this requirement when we are writing a higher order function. So for example, if we have a count function, supposed to count how many elements in a list satisfies some predicate. Maybe we have a list of students, you want to count how many students pass. Then we can write a signature where we require that the predicate has no effects. Now, why would we want to do this? There can be different reasons. One could be that maybe we want to be able to evaluate this in parallel. Then it wouldn't be good if there were side effects because their order could get messed up. Another reason could be that if we have some collection that doesn't have a stable ordering inside, like a hash set, we might want to not leak that detail. So there can sort of be different reasons for enforcing or requiring purity. Okay, but without effects, it's not so interesting. It's still useful, but we also want to actually have some effects in our language. So one effect we can have is the I/O effect. And that basically sort of means this program can do anything. We'll get back to that in a little bit. But just to show an example of our first effectful function, here's say hello, and we give it a string, and then it's going to print to the terminal, and so it has the I/O effect because it interacts with the world. Now, like a type system, a sound type system, the effect system gives guarantees. So ideally, and that's also the case in Flix, we shouldn't be able to subvert it. So for example, if we try to print, but we are lying about the effect being there, we say, well, actually we are pure, well, then our program will not compile. So the effects we have here, we can trust. We can trust those. They're checked by the compiler. Things get more interesting when we have higher order functions. So for example, if we have the map function that we know, maybe we have a list of students and we want to get out a list of student numbers or something. So we want to map the function over that extracts those student numbers. Now normally this function would have some type A to B, and get a list of A's and produce a list of B's. But now for map, we want it to be used with pure functions, impure functions, functions that have some effect. And that means that we actually have to track what f does, and then what f can do, well, that's what map can do. So when we call map with some function that prints, well, that means the call to map itself will also print. And that's where we need these effect variables here. So this ef here and here. This is what's called effect polymorphism. So the compiler, or the programming language, can track that, okay, applying a pure function, well, that's pure. Applying an impure function, well, that's impure. Things get even more interesting and reveal more about the language when we start looking at function composition. So if I'm giving two functions, function from A to B, function from B to C, of course I can put them together. But what if they have two effects? And so in Flix, the language of effects, which is something that's important to ask when you're looking at a language with effects, is how do you combine effects? And so in Flix, we combine them with, they are treated as sets. So here we just say it's the union of the effects of the two functions. And so we're not tracking order, but we get the union. So for example, if one function was pure and the other one had I/O, then the whole thing will be I/O. If one was non-deterministic and one was I/O, then the resulting function would be non-deterministic and I/O. And of course, there's a large language design space here, but we think sort of reasoning about sets is something that programmers will be familiar with. Going a bit further, I talked about sometimes you want to actually prohibit effects. So one example could be when we have an exception handler, it would not be good if the exception handler itself can crash. Maybe we want to disallow that. And so we can actually do that. So let's say we have some on-exception function, we register an exception handler, then we can say ef minus throw. Now how should such an effect be understood? Well, you can choose ef any way you want, but we're going to subtract throw. So in other words, this means that f here can do whatever it wants, but it just cannot throw. So it could be a pure function, it could print something, it just can't throw. So this we call effect exclusion. Another thing, just to illustrate the same example, is maybe we have a UI and we're attaching some mouse handlers, and then we could have a block effect. The idea being that it's not good in the UI if you, for example, you press a button and then you start accessing the network because the UI will freeze, right? So you should instead do that computation in the background, but not freeze the UI thread. So here, if we tag operations that may block, then we can say, okay, installing a mouse handler is, with a block effect is not allowed. So that will be a compile time error. Okay. So one thing is, sort of what is the language of effects? And so in Flix, we've seen that it's actually sets. We can have unions of effects. We can subtract effects. In fact, we can also have disjoint unions and intersections and these kinds of things. But another important question is, what are actually the effects that are built into the language and that come with the standard library? And so this question is a bit like saying, well, if you're programming some language, what are the primitive data types? Right, so if you know Java, for example, well, there's integers and booleans and so on. There's also some types from the Java standard library, right? There's like string and array list. And finally, you can define your own types. You can write like a class student or a class giraffe and so on. So when thinking about effects, the same kind of design space opens up. So the language needs to come with some primitive effects. And in Flix, there are actually two. So there's some primitive effects and some heap effects. They're built into the language. Then there are some library-defined effects. In some sense, they're built in because the language ships with the library, but they're still, inside they're defined in the language itself. So that's like your array list, for example, if it was Java. And then also programmers need a way to express their own effects. So we call those user-defined. Now these are the primitive effects in Flix. And it's a really good question what a sort of good set of primitive effects is here. And this is probably not sort of the final word on what is going to be in Flix. On the one hand, there is a tendency to want to keep it very small, but on the other hand, so you could just have I/O. As you say, the primitive effects are just either purity or I/O. Or you could try to have it very fine-grained. But in Flix, we have a very small set of primitives and with a view towards security. So basically, we're trying to say that there are very harmful effects. So for example, like creating new processes is very harmful, whereas non-determinism is not that harmful, at least immediately. So this is like the base layer of effects. Actually, you won't see these effects that much. You will just write your program, and you will mostly be using effects from the library, which we'll get to in a moment. And these may only be sort of in the signature of main. So it's not that you see these too much. But they are kind of the ground truth of what your program can do. So for example, if your program does not have the exec effect, if main does not have that effect, then you will not create new processes. Another very important kind of effect built into the language is heap effects. So these are for dealing with mutable memory. And the key idea here is simply that, imperative programming is okay. Writing my function, and maybe for some performance considerations, or maybe just from style, I want to do some imperative programming with pointer manipulations and changing mutable data structures. But if that mutable memory is confined to the scope of my function, in other words, when my function exits, if that mutable memory becomes unreachable, then my function is actually pure as seen from the outside. And so this is something that we support. If you're familiar with the ST-monad, there are strong connections there. But here's the way it looks in Flix, and just to illustrate an example here, let's say we wanted to sort a list, an immutable list. Well, we could sort it functionally, but a better approach might be to take our list, convert it to an array, a mutable array, then sort it in place using a quick sort or something like this, where we're mutating the positions of the elements, taking the array and then converting it back to a linked list. And so this means that here we say like a lexical scope begins. There's a region capability here. We heard about capabilities earlier. And that allows us to create this array that now belongs to RC. Then we can do the sort, and we can convert it back to the list. And once this scope exits, the compiler enforces that all this mutable memory is no longer accessible. And so this gives us the best of both worlds, because we can get the good performance and perhaps the style if we like it, but people who use sort, they don't know about it. Just to give you a bit more intuition, here's another example. So here, again, I say a region begins. I have this capability. Here, capability is just permission to allocate mutable memory in that region. I create an empty mutable list, and then I'm doing side effects on it here, adding animals. And then I'm popping the last thing added to the list and printing it. And so all of these statements here, they have some heap effect that's somehow associated with RC. So inside here, for sure, we are not pure. Inside here, effects are happening and we're tracking them. Then at the end here, we have both the heap effect and I/O, but now the scope closes, and so we're only left with the I/O effect. The I/O effect is still there because we do print, so we are not pure. Looking at the API of this mutable list, it's like array list, also reveals something about the behavior of this API. So, for example, we can see to create an empty mutable list, we need this capability. It's called region here. It's like a region capability, and then we'll have some effect in that region. Same for, and we can see, more importantly, that every mutable list has some element type, could be a list of students again, and then it has some associated region. When we're pushing onto such a list, of course the element type must match the list type, and then we get an effect in the associated region. So all these operations, of course, are changing the list. When we get to count, it gets a little bit more interesting, because now we have the effect of the function we're counting with and the heap effect of the region. So here we get EF plus, or union, the heap effect of R. So in summary, these heap effects and these regions and capabilities allow us to be imperative programmers, but sort of confined. So we get the best of both worlds. And I would argue this is also kind of necessary. There are simply certain things where it's not efficient to use a functional implementation. Just see how am I doing on time? Oh, yes, okay. So let's talk about, so when you add effects to a language, those effects are it's not a very orthogonal feature. It's going to pop up everywhere, forcing you to make decisions sort of affecting the whole language. So let's look at a different aspect of Flix and see how effects come into play. So let's say that in Flix we can write two functions to add numbers. So we can add integers, okay, and we can also add floating point numbers. Yeah, that makes sense. You have those two signatures. It would be nice if we could abstract over addition, right? Because adding integers and adding floats is sort of, the same thing, or a similar thing. And so we can use a type class. So we call it trade in Flix, because Flix is a JVM language, so calling it class would be pretty confusing. So we call it trade, but it's a type class. That is polymorphic over t, and saying, if there's some instance for t, then we can add numbers and get a t back. Then we can implement instances for integer 32 and float 32. And then we can overload the plus symbol to mean add.add. So these are kind of standard techniques. It works well. But once we have effects in our language, a problem occurs. So what happens if there's division? Well, the problem is that integer division can give division by 0 errors. This is how it is on the JVM at least. Whereas floating point division by 0 is actually okay, because you just get nan. So now what we have is that we have an abstraction adding two things, but they have different effect behavior. So it would seem we can't abstract over these two things. They cannot be made part of the same type class because the signatures differ. So how can we solve this? So this is where we have the idea of an associated effect. So it's like a type member, you could say, where we say that actually the add type class has an associated effect, here called AEF, and when you add two things, you also get this associated effect. And then the instances will specify what that effect is. So for integer addition, well, that's where we have the division by 0, and for float, there's nothing, it's pure. So associated effects actually allow us to abstract over these two different behaviors. I have a more complicated example here to show that, for example, when you're indexing into things, like, you have an array and you're like A and indexing with some index, then both associated types and associated effects come into play. You can index into a list, then the index is a number, you get a T out, and you get maybe out of bounds exception. You can also index into a mutable map. Then the index is not an integer, but just the key of the map. And then you get both the heap effect and out of bounds if the key doesn't exist. In this case, because we decided not to return an option here. Okay, so that was associated effects, and it's just I show this to illustrate that adding effects also means thinking about the abstraction mechanisms in your language. How will they interact with effects? And we use these when you want to abstract over partial and total functions. That was the division example. But also abstracting over mutable and immutable data, because mutable data has heap effects. So we need to deal with that. And also in general when abstracting over resources. So different kinds of sockets and files and these kinds of things. Then lastly, I'll talk about effects and handlers. So I don't know how many of you are familiar with algebraic effects or those kinds of things, but I'll try to introduce it in 3 slides, which is a little bit too little, but we'll see how it goes. So at a very high level, the idea is that we are all pure functional programmers, and but our functions still depend on the external world. Maybe a bit more concrete, our functions often have some indirect input and some indirect outputs. And so really we want to sort of be functional programmers modulo some effects. And so we will express these effects as interfaces, we could call them, but they're called effects. And then we will have the type and effect system track wherever we use them. And then to give them meaning, this is the important part, we will install things on the stack saying, well, when this effect occurs, then this code should be executed. So it's a little bit like having an interface and implementing it. But instead of implementing it, let's say, globally, for the whole program, or implementing it by some object that has to be passed around. Here it is where we are on the stack that determines the implementation. And this has allowed us to sort of swap out the meaning of these effects. So very concretely, maybe we have one set of handlers we use for production. So that's where the effects actually happen and actually talk to the database or the network or whatever. And then we could have another implementation where we sort of mock it. So instead of talking to the network, you talk to some fake server where we control the data. And so, so I have this huge piece of code. It's the last piece of code I will show. So this is sort of more or less idiomatic Flix. So we are just accessing some URL, then we're logging things. Accessing the network can go wrong, so we have some error handling, and we do more logging, and we write to some file, and so on. The important point here is down here. Like normally a program is not like just one main function, right? So normally, of course, this would be separated out in lots of functions that call each other. But the point is that this long blob of code ultimately leads the ability to write to the file system. It needs to do some HTTP, and then there's some logging. And so here at the end, in this case, for this example, I'm saying, I want to do all of these by actually using a handler that actually does those actions on the JVM. So actually executes the network things and the file writes and so on. But the point is that I could also install a different handler. So for example, here I am installing a different handler for HTTP. And what I'm going to do is saying, the connection is always failing. So this allows me to swap out the implementation. So that's effect handlers. So they encourage modularity because it's pure functions modulo, some effect behavior that we can change, right? And because we can change it, we can reuse it in different contexts. Because we can also swap out that behavior, it's easier to test because we sort of get both dependency injection and mocking for free. Okay, so that was the effect part. I want to say a little bit more about, so to recap, Flix is an effect-oriented programming language. We talked about there's not only a type system, but an effect system. We use these effect set formulas to talk about effects, right? So we had unions, intersections, subtraction, and so on. There are variables in there. We have these primitive effects, which saw like accessing the network file and so on. Then we saw heap effects, allowing you to do mutation in a controlled way. We saw effect handlers, allowing you to reinterpret certain effects and implement your own effects. For example, HTTP is not a primitive effect. It's something defined in the library. And the meaning, the default handler is also given in the library that accesses the network. We saw effect polymorphism. There was this idea that when you have a function like map, its effect behavior depends on its argument. And we saw effect exclusion, which allows us to prohibit certain effects and have that statically enforced. And lastly, we saw that effects also have to interact with type classes in a certain way, because sometimes we need to abstract over different effect behavior. Okay, so that was the effect stuff. I just want to show one more thing, because there's one other interesting feature in Flix, at least one other interesting feature. So we're just completely going to shift gears here for a moment. So I'm from Aarhus here, and so this is the selection of airports I can fly to, which is not that great a selection. But of course, I can fly to London, right? And then from there, I can fly to somewhere else. And so the point is that how can we implement this, right? This is some graph reachability problem. And Flix, in addition to being an effect-oriented programming language, actually also has a logic part to it. So I just wanted to show you, just in one slide, something completely different, which is that in Flix we have sort of embedded logic programs, specifically this Datalog formalism that is very useful for graph queries. Because as someone was commenting on, functional programming is really excellent for working with lists or trees or these kinds of things. But when it comes to working with graphs, things get more complicated. And this is where Datalog shines. So just to show you very briefly, if we want to compute, I'm in Aarhus. I have a list of edges here, like, Aarhus, I can go to London, right? And from London, I can go to Rome, and I don't know. And then we want to compute what are all the cities I can fly to transitively. Well, that is elegantly solved by Datalog, so we can have a small Datalog fragment here, and then sort of link style from C#, but I would say more powerful. We can have this recursive logic program and solve it and get the answer out as a list. Okay, don't worry too much about that. That was just sort of a quick side comment. I hope you think it's cool. Yeah, so we have embedded Datalog also in Flix as one of its unique features. And this leads me maybe to sort of a high-level point about this Flix programming language that we're building. And I should say we're trying to build a real language that we hope ultimately some people will use and find useful. And one sort of high-level design philosophy here is that it is a functional language in the sense that we write functions and compose them together. But it's okay if those functions use some effects that we can define. It is also okay if those functions internally use some mutation, as long as it's confined. And it's also okay if those functions internally are expressed as logic programs. So everything is functions, but the implementation can vary depending on what we're trying to do. Okay. So this is actually a big effort that's been going on for some time. So I just want to show you a little bit of the stuff we have already. There's a website, flix.dev. You can go to get a quick glance of the language. We have a playground, like the Rust playground, where you can go and write programs. It's running on a shared server, so please don't write a Bitcoin miner. But although it would be cool if someone wrote a Bitcoin miner in Flix, so I'm kind of torn. So actually, maybe do go and break it, and then we have some cool programs, right? And you will have to use effects because you will need access to the network. So yeah, so that would be cool. We have a VS Code integration. We implement almost all of LSP. This is also something I'm quite proud of and worked a lot on. So our LSP implementation uses the real Flix compiler. And that means that we have to rethink how we write compilers because it should still work if there's, we can't even parse the program, there are type errors, name errors, and so on. So our compiler is fairly resilient. So even the errors in the program, we can still actually handle it. And by the way, by using the real compiler, we have this advantage that if you ever get an error in the tooling, like in VS Code or your editor, well, it's a true error because it's coming from the real compiler. There's not two separate implementations. Here is NeoVim. There's a book also describing the language, which is not accessible to people who are not programmers, but to people who already know some programming and are maybe functional programmers. There's also a standard library. This is more or less what you would expect. It's still fairly small, but it's about 40,000 lines of code, so I think it's bigger than the OCaml standard library, but it's nothing compared to Haskell or Java, of course. The most interesting thing about it is that there's a full collection library, and it's subject to the effects system. So everything is typed with the effects system. And also the standard library doesn't just have data types and functions, it also has effects. So we're sort of expanding the set of built-in effects. Recently we were adding a lot of network stuff. Yeah, it's open source, it's on GitHub. Remember, go and start so we can get those stars, important. Yeah, we've implemented almost all of LSP. Right, another thing that I think we're also pretty proud of is that we tried to be parallel from the beginning. So all our compiler phases are parallel. It's still a phased compiler, which is a limitation, but you really get a lot out performance-wise of basically everything is working on the program in parallel. This is just the front end. Actually, there are like 28 compiler phases, but they all operate in parallel. Yeah. Okay, so I think I'm doing well on time. Yeah. So to wrap up, just to say this is not just my work, it's the work of students working tirelessly and open source contributors. It's a big thing. I mean, you can see we have 250,000 lines of code. It's also a collaboration with Copenhagen University, University of Waterloo, and University of Tübingen. Also, this does not stand alone. We're building on a long research tradition in regions, in effect systems, type classes, in logic programming. And then we're adding our own contributions on top. So if you sort of care about some of these features, the details of how does the effect system work and interact with type classes, how do we do type inference is a big sort of research problem. You can go and look at that. So to summarize, so Flix is I want to say a real programming language. We're at least building it to be a real programming language. We're getting close to a version 1. So it would be great for you to try it out. We have a unique combination of features, so I think the effect-oriented thing is the big thing, but there's also some cool logic programming in there if that could have your interest. We have sort of features you would expect. We compile to the JVM, it's plenty fast, and we have invested a lot in tooling, so we have great VS Code support. We have both a parallel and incremental compiler. So that's it. Thank you so much for your attention.
Thank you for this. Do we have any questions?
So when you were talking about your heap effects, I wasn't quite clear on whether or not reading from the heap was an effect. You didn't seem to have different read and write effects at any rate.
Yeah, great question. Yeah, so first of all, yes, you're correct. At the moment, sorry, now I have to go back a lot of slides. At the moment, we are not distinguishing between reads, writes, and allocations. And so the short answer for that is that we are being a little bit conservative here in that we can design sort of very expressive effect systems, but we also want people to adopt them. So we're a bit afraid of having very complicated signatures. I think this also goes to, this work on, for example, capabilities and so on. Will we be able to teach programmers to use these languages if they have very complicated types and effects? So yeah, so for now, there's only a heap effect conflating, not distinguishing reads or writes. A slightly longer answer is that we're actually working on a new system where you can choose the granularity. So basically, when you create a mutable list, you would say, I only want the heap effect, or you would say, actually, please split all the effects into alloc, read, and write. And then you sort of opt into some additional complexity, but you also get more precise knowledge. Yeah, good question, thanks.
Okay, who's next?
Thank you for the talk. Perhaps I missed it, but do you have anything related to parallelism and concurrency in the effects per se? Yeah.
I don't think we have a good story for that, no. The only thing I can tell you is that right now we do not allow heap effects and algebraic effects to cross a parallelism. Like you cannot, when you spawn an expression, all its algebraic effects and heap effects must be local to that. So you cannot have algebraic effects crossing between threads or heap effects. But I would like to have sort of a more detailed story to tell you, but I don't have it yet.
What is the most biggest or complicated program you have implemented in Flix?
Yeah, great question. I think two. So one is the standard library, which is a quite extensive collection library. It's larger than OCaml's standard library, if you count the lines or functions. It's like 3,500 public functions. And then we have, because of the logic language, we have a full-blown Datalog engine implemented in Flix. And this Datalog engine has lots of Datalog stuff. So it has like implementation of sim and naive evaluation. It's like a lowering pass to the RAM. It has parallelization. So yeah, so I think the Datalog engine is the biggest and most complicated Flix program. It's maybe 5,000, 6,000, 7,000 lines of code. Then there are also other people who are sort of, we have one commercial user who's using Flix, but he doesn't want to say what he's using it for other than data analytics, because in his words, they are Microsoft shop, and so they don't, he's going under the radar. And then we have, people have implemented kind of fun stuff that you do in functional languages, interpreters, all kinds of things, JSON parsers, yeah.
Okay. We have plenty of time, so don't be shy.
There's a question down here.
Yep. Okay.
So as an academic, the thing that's most impressive about this is you clearly have a large contributor base, lots of tooling. How did you do all that as an academic?
Yeah, it took a long time. I've been working on this for like 8 years, and then sort of trying to slice it into some good projects that student can work on. But also, if you take a longer perspective, for example, the standard library, it's these 40,000 lines, that's a really big code base now subject to what you could call a traditional effect system. And for example, so we use something called Boolean unification for inference, and so I think this is the largest application of Boolean unification in the world. So you can do some empiricism now, because it's not like a, of course it started out being just one file with a simple interpreter, but now because it's a full system, there's a lot of data we can collect and we can sort of look at things. So yeah, so it's a huge upfront cost and you have to plan for it, but I think it pays off a bit down the road. That would be the answer to the question, how do you justify doing this as an academic? Also because I want to. It's what I want to do.
So I saw you have these effect handlers and you can plug it in for testing and production, which is great. Are they lexically scoped or are they dynamically scoped?
They're dynamically scoped.
Ah.
And yeah, and there's a long discussion about that, yeah. And they're also multi-resumption, which is either good or bad, depending on, yeah. And so actually, so we went for something very general there, and we probably did that because we were leaning a bit more on the academic side and less on the user side. And it also means we have to compile to complicated JVM bytecode. Yeah. Actually, maybe I have a comment to resume on that. So, Martin talked about capabilities, right? And now I'm here talking about effects, which are sort of two sides of the same coin. And in both systems, you have to make really big language design choices. And there's this problem that, I'm just making these decisions at home, sure, surrounded by PhD students and colleagues. But, how can we know, ultimately, how people will be using these things and that we designed them correctly? I think that's a really hard question. It's not like we can do could we conduct a study of 1,000 programmers? It's hard to know. So yeah, so when it comes to effects, we have to make all these choices, and with Flix, we're just sort of throwing darts where we think it's right. Sure, we think about it a lot and talk about it, but are they the right choices? Only time will tell.
Hello, thanks for the talk. So, since you are slowly getting into version 1, I was wondering what are the work needs to be done and what are the further steps beyond that?
Yeah, thanks. Good question. Well, I have like a long mental list, like a laundry list. But I think, a little bit more stability here and there in the compiler. I think a little bit better integration with Java in certain areas, in generics and so on. And then, of course, the fear of pushing the button. When is the good time to push the button? So some of the original Rust authors also had this discussion, and they couldn't decide when to release version 1, because chicken and egg problem, right? Once you say it's version 1, people expect some stability. But then what about all the great ideas that we can? And so they said that at some point they just did it. So I'm thinking at some point we also will want to do it, but maybe we also need to think about some versioning scheme or whatever. Rust has been really good at this, but I don't know, there's so many technical challenges to doing that. But actually we're quite close. Yeah, I just haven't pushed the button yet because there's just one other thing I want to.
Okay. Any more questions? We should have a runner.
I might have missed it, but in terms of interop with Java, how are effects handled? Say, for example, you write to a file and you don't specify that the function has I/O.
Yeah, great question. The answer is kind of complicated. So, and I will start by answering it by starting in a little bit of a different place. So we're also building a package manager for Flix. And basically, there are going to be three levels of Flix programs. They're going to be pure Flix programs, not pure, plain Flix programs only written in Flix. And for those, we have all kinds of nice properties. Then there is going to be Flix programs that make use of the Java library. And for there, we have to annotate the Java library with these primitive effects. So for example, if you create a file input stream reader and whatever, we will have annotated it actually with the fs read effect. And of course, now you have to trust that our annotations are correct and also that the Java standard library is not malicious. For example, that the documentation of Java actually it does what it says. So then you can be programming with Flix plus the Java standard library. And then these things should still hold and be tracked and all these things. Then there are certain rules, like you can't interleave algebraic effects with sort of callbacks in Java, and it's a long discussion there. And then finally, there's going to be something which is like Flix plus arbitrary jar files. And then like you can do that, and you just get the I/O effect, but is that right or not? Anything can happen. But the hope would be, of course, the ecosystem would mostly be plain Flix. And also the idea is that, and I think that this is also a very general idea many people have pursued, right, is that you write sort of your core program, and you have some effects, and then on the edges of the program you have handlers, and maybe those handlers are written in Java, or not written in Java, but use the Java APIs. And that's also in this example here. These guys down here, they're part of the standard library, and they call Java to get their work done. But this code here, up here, is of course just a Flix program.
Anybody? Okay, so one more round of applause.